Hello there, and welcome to Sleepy Science Vault. There is a place on this planet that no human eye has ever seen. Not a distant continent, not a hidden valley, not some far corner of a foreign wilderness, but right here, beneath the surface of our own world. Beneath the waves. In the dark, quiet, impossible deep. 95% of the ocean remains unexplored. Think about that for a moment. We have mapped the surface of Mars with greater detail than we have mapped the floor of our own seas. The ocean is not a mystery of the past, it is a mystery of right now, alive and ongoing, surrounding us on every side. 60% of this planet is covered by deep sea. Not beach, not shoreline, not the sunlit shallows where children play, but deep, open, pressurized ocean, stretching far beyond what light can reach. And of all Earth's marine environments, 90% belongs to the deep ocean alone. The shallow world we know, the coral reefs and tide pools and kelp forests, that is only a thin ribbon at the edge of something vast. At the very bottom of that vastness lies what scientists call the Hadal Zone. Named after Hades, the underworld of ancient mythology. It is one of the last true frontiers remaining on this planet, and for most of human history, we had no idea it even existed. Below 1,000 meters, sunlight disappears entirely. Not dims, disappears. The ocean becomes a world of permanent, absolute darkness, a blackness so complete that no amount of time would allow your eyes to adjust to it. There is simply nothing to see, only depth, and silence, and cold. And yet, life found a way down there. On the abyssal plains, those vast muddy seafloors sitting 3,000 to 6,000 meters below the surface, entire ecosystems exist. Strange, patient, slow-moving communities of creatures living on falling particles of organic matter drifting down from the world above. They have never seen sunlight. They may never move more than a few feet in their entire lives. And yet they are there, quietly alive in the dark. The pressure at those depths is staggering. At 3,000 meters, the weight of the water above you is 300 times greater than the air pressure we experience on land. It would crush a human body instantly. It would collapse most machines we build. And yet the creatures that live there carry that pressure as naturally as we carry the weight of the sky. Still, even at those depths, the ocean is never truly still. Distant submarine mountains shift deep currents. Long-distance waves, invisible from the surface, travel through the water column and stir the deepest parts of the sea. The abyss breathes, in its own slow and ancient way. And at the very deepest point of all, 36,000 feet down, at the bottom of the Mariana Trench, sounds can still be heard. The low rumble of distant earthquakes. The movement of water. The faint, traveling vibrations of a world far above. Even there, in the most remote and silent place on Earth, the ocean is listening. The ocean has a language. Not a language built from words or symbols, not something you could write down or translate into any human tongue, but a language of pressure and vibration, of waves moving through water at speeds that seem almost impossible from where we stand on dry land. Sound travels nearly 1 mile per second in the ocean. In open air, that same sound would move at roughly a third of that speed. Water is denser, more connected, more responsive to the slightest disturbance, and so when something makes a sound beneath the surface, that sound doesn't simply fade and vanish the way it might in a room or an open field. It travels. It carries. It reaches places that seem impossibly far away. There is a layer in the ocean, sitting at a specific depth where temperature and pressure combine in just the right way, that acts almost like a natural sound highway. Scientists call it the SOFAR channel, the sound fixing and ranging channel. When sound enters this layer, it becomes trapped. It can't rise above it, and it can't sink below it. Instead, it travels horizontally, spreading outward in all directions, losing very little energy along the way. Through this channel, the low moans of baleen whales have been detected thousands of miles from where they were made. A single whale, swimming somewhere in the North Atlantic, can be heard by another whale in waters closer to the equator. The ocean doesn't just allow that communication to happen, it assists it, shapes it, carries it along. And it isn't only whales using this channel. The deep hum of large cargo ships, engines turning slowly far above, sends vibrations downward that enter the SOFAR layer and travel with the same effortless distance. Seismic rumbles from shifts deep in the Earth's crust move through it. The ocean becomes a kind of record, holding all of these sounds at once, biological, mechanical, geological, layered together in a continuous low conversation that has been going on, in one form or another, for millions of years. Beneath the seafloor itself, undersea volcanoes add their own voice to this world. They don't erupt the way volcanoes do on land, with fire and ash and the violent movement of air. Underwater eruptions are slower, more pressurized, more muffled, and the sounds they produce travel outward through the water like the beating of a very slow, very deep drum. Scientists monitoring hydrophone arrays, underwater microphone networks originally designed to detect nuclear tests during the Cold War, have captured these volcanic rumbles from hundreds of miles away. The Earth is always speaking down there. Most of the time, no one is listening. The landscape of the deep ocean shapes its soundscape just as much as the creatures within it. Undersea canyons, those dramatic geological formations carved by ancient currents and tectonic movement, don't allow all sound frequencies to pass through them equally. Certain tones are absorbed, or reflected, or simply blocked. A canyon wall becomes a kind of acoustic barrier, creating zones of near silence in its shadow and zones of unexpected resonance on the other side. The deep ocean has its own acoustics, its own architecture of sound, built from geography as much as from biology. And then there is light. In a world where sunlight cannot reach, where sound is the dominant sense for the creatures large enough to use it, many of the smallest and strangest inhabitants of the deep have found another way entirely to communicate. Bioluminescence, the ability to produce light from within the body, is not rare in the deep ocean. It is, in fact, remarkably common. Estimates suggest that the majority of deep-sea animals are capable of producing their own light in some form. A flash of blue-green light in total darkness can mean many things. It can be a warning. It can be an invitation. It can be a lure, designed to attract prey towards something patient and waiting in the dark. Some species produce patterns of light so specific that they are believed to function as individual identification, a bioluminescent signature that says, in effect, I am here, I am this species, I am this individual. In a world with no color, no sun, no visual landscape of any kind, a single cold point of light carries enormous meaning. And silence, in the deep ocean, can be just as communicative as sound. Many predators of the deep have learned to exploit the zones where sound is naturally suppressed, areas in the acoustic shadow of canyon walls, or below certain thermal layers where noise from above simply doesn't penetrate. These animals don't just hide in darkness. They hide in silence. They move into acoustic dead zones and wait, utterly still, for prey that navigates by sound and has no way of sensing that something is already there. The absence of noise becomes a tool. A trap. An ambush built not from physical cover but from the simple, patient absence of vibration. Even the earliest stages of life in the ocean are shaped by sound. Marine larvae, the microscopic young of fish, crabs, corals, and countless other species, spend the first part of their lives drifting in open water, carried by currents with almost no ability to direct their own movement. And yet, when the time comes for them to settle, to find a reef or a rock or a stretch of seafloor to call home, many of them are guided by sound. Healthy coral reefs produce a distinctive acoustic signature, the crackling of snapping shrimp, the low calls of fish, the constant gentle movement of life. Larvae detect these sounds and move toward them. A reef is not just a physical structure or a chemical signal. It is a sound. And young animals follow that sound home, across distances that seem remarkable for creatures barely visible to the naked eye. Even the smallest forms of ocean life contribute to this world of sound. Plankton blooms, those vast explosions of microscopic organisms that sometimes turn the surface of the ocean green or blue or rust red, produce a faint but measurable background noise. Individually, a single plankton organism makes no sound a human instrument could detect. But collectively, in the billions, the gentle movement of their bodies, their feeding, their reproduction, creates a kind of biological hum. A soft, diffuse murmur that rises and falls with the seasons, following the light and nutrients that drive these blooms across the surface of the sea. All of this, the whale calls, the volcanic drumming, the bioluminescent conversations, the acoustic ambush zones, the sound-following larvae, the quiet murmur of plankton, comes together into something that scientists now recognize as one of the most complex acoustic environments on the planet. The deep ocean is not quiet. It never was. Long before the first ship ever crossed the surface, long before the first submarine ever descended into the dark, the ocean had its own soundscape, layered, ancient, and ongoing. A world of voices that had nothing to do with human language, and everything to do with survival, communication, navigation, and the slow, continuous pulse of life in places we are only now beginning to understand. Beneath every weather forecast, beneath every shift in season, beneath the warming of summers and the bite of winter cold, there is a system at work that most people will never think about and almost no one will ever see. It moves without sound. It carries no visible current on the surface. It has no single point of origin and no single destination. And yet it influences the climate of every continent on Earth, moderates temperatures across entire ocean basins, and has been running, more or less continuously, for millions of years. It begins with the ocean itself, not as a single body of water, but as a layered one. The ocean is not uniform from surface to floor. It exists in 3 distinct layers, each with its own character, its own temperature, its own relationship with light and pressure and life. At the top is the sunlit zone, warm and active, stirred by wind and weather, home to most of the ocean life we recognize. Below that lies the twilight zone, where temperatures drop sharply and light fades to almost nothing. And deeper still is the abyss, cold, dark, and extraordinarily stable, where temperatures hover just above freezing and almost nothing changes from one century to the next. These layers don't mix easily. The boundaries between them are real physical barriers, created by differences in temperature and density that resist the kind of casual mixing you might see in a glass of water. And yet, over long timescales, they do mix, driven by forces that begin not with temperature alone, but with something far less obvious. Salt. Seawater is not simply water. It is a solution, a careful and complex mixture of water and dissolved minerals, and the concentration of those minerals, what scientists call salinity, varies across the ocean in ways that shape everything about how it moves. On average, ocean water contains somewhere between 34 and 36 parts of dissolved salt per 1,000 parts of water. That range might seem narrow, but within it lies an enormous amount of variation, and that variation is anything but random. It follows patterns set by evaporation, precipitation, river runoff, and the freezing and melting of ice. Each of those processes either adds or removes fresh water from the ocean surface, and in doing so, either concentrates or dilutes the salt that remains. In the tropics, where sunlight is intense and evaporation is high, surface salinity reaches its peak. Water evaporates quickly, fresh water rises into the atmosphere as vapor, and the salt stays behind, making tropical surface waters measurably salter than those at higher latitudes. The warmth of the tropics doesn't just heat the water, it effectively concentrates it. Near the poles, the opposite is true in a different way. The Antarctic waters surrounding the southern continent receive relatively low levels of evaporation, and large amounts of fresh water enter from melting ice and precipitation, keeping salinity lower than in the tropical ocean. These southern waters are cold and dilute, a very different character from the warm, salty seas near the equator. In the North Atlantic, there is a patch of water that oceanographers have studied with particular interest for decades. This region is notably salty, salter than much of the surrounding ocean, and that saltiness is not an accident. The North Atlantic loses enormous amounts of water to evaporation, much of it carried by prevailing winds toward Europe, contributing to the relatively mild and wet climate of Western Europe. What is left behind is dense, salty, heavy water, and that density is going to matter enormously in a moment. On the other side of the world, 2 neighboring seas tell a story of remarkable contrast. The Arabian Sea and the Bay of Bengal sit on either side of the Indian subcontinent, similar in latitude, similar in many surface conditions, and yet dramatically different in salinity. The Arabian Sea is significantly salter, shaped by high evaporation and limited freshwater input. The Bay of Bengal, by contrast, receives the outflow of some of the world's great rivers, including the Ganges and the Brahmaputra, and experiences heavy monsoon rainfall. The result is a surface layer of relatively fresh water that sits above the salter water beneath, creating a stability that affects everything from monsoon dynamics to the behavior of cyclones forming in the region. Two seas, side by side, shaped by the rivers and rains and winds of an entire subcontinent. And then there is ice. When seawater freezes, when temperatures drop far enough for the surface of the ocean to solidify into sea ice, something remarkable happens to the salt within it. Ice crystals are made of pure water. As the ocean surface freezes, the water molecules lock together, but the salt they were dissolved in has nowhere to go. It is expelled, pushed downward into the water immediately below the forming ice. The result is a pocket of extremely cold, extremely salty, extremely dense water just beneath the growing ice sheet. This is not a small effect. In the waters around Antarctica, and in parts of the Arctic, the formation of sea ice each winter produces enormous volumes of this cold, dense brine, water so heavy that it sinks, slowly and inexorably, toward the ocean floor. It doesn't sink dramatically. There is no visible cascade, no roaring underwater waterfall. It sinks the way cold air settles on a still night, quietly, continuously, driven by nothing more than its own weight. When spring comes and sea ice begins to melt, the process reverses. Fresh water is released back into the surface layer, diluting the salinity of the surrounding ocean and creating a lighter, more buoyant layer at the top. This seasonal rhythm, freezing and releasing, concentrating and diluting, pulses through the polar oceans with the regularity of a heartbeat, influencing the density structure of the water column season after season, year after year. All of these variations in salinity, combined with the temperature differences between tropical and polar waters, create differences in density that are subtle by any ordinary measure, and yet powerful enough to set the entire ocean in motion. Warm water is less dense than cold water. Fresh water is less dense than salty water. Cold, salty water is the densest of all. And in the ocean, density determines where water goes. Dense water sinks. Less dense water rises to take its place. And this constant movement, driven by temperature and salinity together, which is why scientists call it thermohaline circulation, from the Greek words for heat and salt, creates a system of deep ocean currents that links every ocean basin on the planet into a single, continuous flow. The dense water forming near the poles sinks to the ocean floor and begins a slow journey along the bottom of the sea, moving through the deep basins of the Atlantic, spreading into the Indian and Pacific Oceans, gradually warming and rising back toward the surface over centuries, and eventually flowing back toward the poles to complete the cycle. The entire circuit takes somewhere between 500 and 2,000 years to complete, depending on which part of the system you're following. This is what oceanographers call the global conveyor belt. It is one of the most important mechanisms on the planet for distributing heat, and it operates in complete silence, completely invisible from the surface, far below the reach of any wind or wave. It carries warm surface water toward the poles, moderating temperatures in places like northern Europe that would otherwise be dramatically colder given their latitude. It carries cold, nutrient-rich water up from the deep in regions of upwelling, feeding some of the most productive fisheries on Earth. It moves oxygen from the surface into the deep ocean, sustaining life in places that would otherwise suffocate. And it moves carbon, enormous quantities of it, downward into the deep sea, where it stays locked away for centuries, playing a quiet but significant role in regulating the composition of the atmosphere above. None of this is visible from the shore. Standing on a beach, watching waves come in, you would have no way of knowing that the water in front of you is part of a system so large it takes 2,000 years to complete a single cycle. You would have no way of sensing the deep cold currents moving beneath you, or the slow upwelling of water that left the surface somewhere near Greenland 500 years ago, or the gradual redistribution of heat that keeps entire continents habitable. The ocean doesn't announce what it does. It simply does it, steadily, continuously, without interruption, the invisible engine of a planet that depends on it far more than most of us will ever realize. There are only a handful of places on the entire surface of this planet where deep ocean water is actually formed. Not hundreds of locations. Not dozens. A handful. Specific, narrow regions where the conditions are just right, where water is cold enough, salty enough, dense enough, to sink from the surface and descend to the floor of the ocean, beginning a journey that will last for centuries. The Labrador Sea. The waters around Antarctica. A few other select regions in the North Atlantic and the Southern Ocean. These are the entry points into the deep circulation of the planet, the places where the surface world connects to the abyss below. From these few locations, deep water spreads outward along the ocean floor, moving through the basins of the Atlantic, rounding the tip of Africa, entering the Indian Ocean, pushing into the Pacific. It moves slowly, not in the rushing, turbulent way of surface currents driven by wind, but in a steady, patient, geological kind of movement that takes centuries to accomplish what a river might do in an afternoon. And yet the volume it carries is staggering. The deep circulation of the ocean moves more water than all the rivers on Earth combined, many times over. As that deep water eventually rises back toward the surface in distant ocean basins, and as warm surface water flows toward the poles to replace what sank, the ocean accomplishes something that no other system on Earth does quite so effectively. It redistributes heat. The tropics receive far more solar energy than the poles. If the Earth had no way of moving that energy around, the equatorial regions would grow hotter and hotter with each passing year, and the polar regions would grow progressively colder. Life as we know it, in most of the places we know it, would be impossible. The temperature extremes would be simply too great. Ocean currents are one of the primary mechanisms that prevent this from happening. Warm surface water flows away from the tropics, carrying its heat toward higher latitudes, releasing that warmth into the atmosphere as it travels. Cold, deep water flows in the opposite direction beneath the surface, completing the exchange. The ocean acts as a vast, slow, planetary-scale heat pump, taking energy from where there is too much of it and carrying it toward where it is needed most. Without this system, Earth would be a profoundly different and far less welcoming place. The western coasts of Europe would be dramatically colder, more similar in climate to the equivalent latitudes in Canada than to the relatively mild, temperate conditions they actually experience. Entire agricultural regions would be unsuitable for farming. The distribution of forests, grasslands, and ice would be different on almost every continent. The ocean doesn't just influence Earth's climate. In a very real sense, it makes the current version of Earth's climate possible. And it does this not only through the movement of water, but through the movement of water into the sky. Evaporation from the ocean surface is one of the primary drivers of weather systems across the entire planet. When sunlight warms the surface of the sea, water molecules gain enough energy to leave the liquid and rise into the atmosphere as vapor. That vapor carries heat with it, what physicists call latent heat, energy stored invisibly in the water vapor itself. As that vapor rises and eventually cools and condenses into clouds and rain, the stored heat is released into the atmosphere, fueling the circulation of air masses, energizing storm systems, and driving the great weather patterns that bring rainfall to continental interiors far from any coast. The monsoons that feed billions of people across South Asia and sub-Saharan Africa are driven in large part by ocean evaporation and the temperature contrast between warm ocean surfaces and heated land. The hurricanes and typhoons that form over tropical waters draw their energy directly from the warmth of the sea surface beneath them. Even the rainfall that fills rivers and replenishes groundwater across inland regions of every continent begins its journey as water evaporated from the ocean. The ocean is not separate from weather. The ocean is weather, in its deepest sense, the source, the engine, and the moderating force all at once. But perhaps the most quietly extraordinary thing the ocean does, the contribution that most people would be genuinely surprised to learn about, has nothing to do with currents, or heat, or rain. It has to do with every breath you take. Nearly half of the oxygen in Earth's atmosphere is produced by the ocean. Not by forests. Not by grasslands or wetlands or any ecosystem rooted in soil. By the ocean, specifically by the microscopic photosynthetic organisms living in its sunlit upper layers, most of them too small to be seen with the naked eye. Phytoplankton. The word comes from the Greek for plant and wanderer, tiny plant-like wanderers, drifting in the surface waters of every ocean on Earth, responding to light and nutrients, blooming and fading with the seasons. Individually, a single phytoplankton cell is almost unimaginably small. Collectively, they represent one of the most significant biological forces on the planet. Like plants on land, phytoplankton use sunlight to convert carbon dioxide and water into organic matter and oxygen. They photosynthesize. And because they exist in such extraordinary numbers, spread across the surface of an ocean that covers more than 70% of the Earth, the sheer scale of their combined activity is immense. Every other breath you take, in a very literal sense, was made possible by organisms you will never see, living in a part of the world you may never visit. But phytoplankton don't only produce oxygen. As they grow, they absorb carbon dioxide from the atmosphere, drawing it down from the air above, incorporating it into their tiny bodies, removing it from the cycle of gases that determines how warm or cool the planet runs. When phytoplankton die, some of that carbon sinks with them, carried downward into the deep ocean where it may remain locked away for hundreds or thousands of years. This process, sometimes called the biological pump, is one of the primary mechanisms by which the ocean removes carbon from the atmosphere over geological timescales. The phytoplankton don't act alone. They are part of a vast and largely invisible community of marine microorganisms that forms the true foundation of ocean life. Not the whales, not the sharks, not even the fish, but the microscopic. Bacteria, archaea, tiny flagellates, single-celled grazers, viral particles cycling nutrients through the water column. This invisible world of the ultra-small drives almost every chemical process in the ocean. It breaks down organic matter. It recycles nutrients. It processes nitrogen and sulfur and iron in ways that influence the chemistry of the atmosphere above. And then there is plankton in a broader sense, all the drifting life of the ocean, animal and plant alike. It includes not just phytoplankton but zooplankton, the tiny crustaceans, jellyfish larvae, copepods, and krill that graze on phytoplankton and are in turn eaten by fish, whales, and seabirds. When oceanographers say that 95% of all marine life is plankton, they are describing a living world almost entirely invisible to the casual observer. The ocean's most spectacular creatures, the ones we photograph and document and celebrate, represent a thin, spectacular layer resting on top of a foundation built entirely from the microscopic and the drifting. Remove the plankton, and the entire structure of ocean life collapses. The fish vanish. The whales disappear. The seabirds have nothing to eat. The oxygen supply to the atmosphere begins to fall. The carbon cycle loses one of its most important moderating mechanisms. The ocean becomes, in the deepest sense, a different ocean, and the planet above it becomes a different planet. This is not a hypothetical concern raised purely for dramatic effect. It is a reflection of just how central these invisible organisms are to the functioning of life on Earth. And beyond what the ocean produces, there is what it absorbs. The ocean has taken on the role of Earth's primary heat reservoir in the age of industrial climate change, a role it did not choose but has fulfilled with quiet and remarkable consistency. Since the mid-20th century, as greenhouse gas concentrations in the atmosphere have risen and the planet has accumulated excess heat, roughly 90% of that heat has been absorbed by the ocean rather than remaining in the atmosphere. 90%. The number is almost difficult to absorb. It means that the warming we experience on land, the rising air temperatures, the hotter summers, the shifting seasons, represents only a small fraction of the total heat the Earth's system has actually accumulated. The vast majority of it has been taken in by the ocean, stored in its layers, distributed through its currents, and held there, slowing the rate of atmospheric warming in ways that have quite literally bought time for life on land. The ocean stores roughly 80% of all the energy currently accumulating in the Earth's climate system. It is, in this sense, the single most important buffer between the current state of the atmosphere and conditions that would be far more immediately and dramatically hostile to the life that has evolved over the past several 100 million years. It does this without announcement. Without any visible sign at the surface of the immense thermodynamic work being done in the waters below. The ocean takes on the heat of a warming world the way a deep lake absorbs the heat of a summer afternoon, steadily, capaciously, without drama. And in doing so, It continues to do what it has always done, in one form or another, across the long history of this planet. It keeps Earth alive. Not metaphorically. Not poetically. Literally, measurably, chemically, physically, the ocean is the mechanism by which this planet remains habitable. It produces the oxygen in the air. It moderates the temperature of the land. It drives the rain that fills the rivers. It absorbs the heat that would otherwise transform the atmosphere far faster than life could adapt. All of it, happening continuously, in the dark and in the light, in the deep cold and in the warm sunlit shallows, quietly, invisibly, without pause. Long before human beings learned to burn coal, long before the first factory sent its smoke into the sky or the first engine turned on a piston of compressed gas, the ocean was already managing carbon. It had been doing so for hundreds of millions of years, quietly, methodically, on a scale so vast that no single number quite captures it. The ocean holds 50 times more carbon than the entire atmosphere above it. Not twice as much. Not 10 times. 50. The air we breathe, with all its carbon dioxide and all its greenhouse warming potential, is a thin and relatively modest reservoir compared to the immense quantity of carbon dissolved in and settled within the sea. To understand why that matters, it helps to think of the ocean not as a passive body of water but as an active participant in the chemistry of the planet, a system that takes carbon in, moves it around, transforms it, and stores it across timescales that dwarf anything in human experience. Carbon that enters the deep ocean doesn't come back quickly. Once it sinks below a certain depth, it may remain there for centuries. In the deepest basins, the storage time extends to millennia, thousands of years during which that carbon plays no role in warming the atmosphere, exerts no pressure on the climate system, and simply waits in the cold and the dark, locked away in the slow, pressurized stillness of the abyss. This is not a trivial function. It is one of the primary reasons Earth's climate remained relatively stable across the long spans of geological history during which life was able to evolve and diversify. The ocean acted as a buffer, absorbing excess carbon during periods of high volcanic activity or organic productivity, and releasing it slowly when conditions changed. The balance was never perfect and never permanent. There were times in Earth's past when that balance shifted dramatically, but across most of the planet's habitable history, the ocean's carbon storage helped keep the atmosphere within a range that complex life could tolerate. And today, in the era of industrial carbon emissions, that ancient function continues. Every year, roughly 3.3 billion tons of carbon dioxide dissolve into the surface of the ocean. That number represents approximately 1/3 of all the carbon dioxide that human activity releases into the atmosphere annually. 1/3 of everything emitted by power plants, vehicles, deforestation, cement production, and every other human source of carbon, absorbed by the sea before it ever has the chance to accumulate in the air above. The process happens at the surface, where ocean water meets atmosphere and gases exchange freely across the boundary. Carbon dioxide from the air dissolves into the water, forming a weak acid, carbonic acid, and beginning its journey into the ocean's chemistry. The rate at which this happens depends on several factors: the concentration of carbon dioxide in the air above, the temperature of the water, the degree of mixing at the surface, and the amount of carbon dioxide already dissolved in the water below. Cold water absorbs carbon dioxide far more efficiently than warm water. This is the same principle that explains why a cold glass of sparkling water holds its fizz longer than a warm one. Cold liquids hold dissolved gases more effectively. And so the polar regions, those cold, churning waters near the Arctic and Antarctic, are among the most important sites of carbon absorption on the planet. Here, at the margins of the ice, where surface waters are being chilled and sinking and replaced by new surface water from below, carbon dioxide moves from air to ocean with particular efficiency. The same deep water formation that drives thermohaline circulation also pulls carbon downward, away from the surface, delivering it into the deep storage of the ocean interior. The polar oceans are, in this sense, double engines, driving both the physical circulation of heat and the chemical cycling of carbon, two of the most important regulatory processes on Earth, operating simultaneously in the same cold and windswept waters. But the physical dissolution of carbon dioxide at the surface is only one part of how the ocean moves carbon into the deep. There is a biological pathway as well, older, more intricate, and in some ways more remarkable. Among the many creatures drifting in the sunlit surface waters of the ocean, there is a group of single-celled algae so small they are measured in micrometers, yet so numerous and so geologically significant that their influence can be seen from space, and their remains have been building up on the ocean floor for hundreds of millions of years. Coccolithophores. They are among the most beautiful organisms in the microscopic world, each cell covered in elaborate, interlocking plates of calcium carbonate, chalk-white discs arranged in precise geometric patterns that vary by species and look, under a microscope, like something between a medieval shield and an architectural ornament. When coccolithophore populations bloom, they can turn vast stretches of ocean surface a brilliant, milky turquoise, visible in satellite images as great swirling patches of pale color against the deep blue of open water. These organisms photosynthesize, building their bodies from carbon drawn from the water around them. And when they die, which they do, in countless billions, every day, their calcium carbonate plates and organic matter sink. Not all at once, not in a single dramatic cascade, but in a continuous, gentle rain of microscopic particles that falls through the water column day after day, carrying carbon from the sunlit surface toward the dark floor of the sea. This is part of what oceanographers call marine snow, the continuous downward drift of organic particles, dead organisms, fecal pellets, shed mucus, and mineral grains that falls through the ocean the way Rayal snow falls through air. It moves slowly, sometimes taking weeks to settle from the surface to the deep seafloor, and as it falls, the ocean works on it. The pressures of the deep ocean are extraordinary. As marine snow descends through thousands of meters of water, the increasing pressure and decreasing temperature change the chemistry of these particles in subtle but important ways. Nutrients locked inside organic matter are squeezed and transformed, becoming available in forms that the microbial life of the deep ocean can access and use. By the time marine snow reaches depths of 2 to 6 kilometers, it has passed through what scientists recognize as a critical zone of transformation. This is where the bulk of the decomposition happens, where the organic material in the falling particles is broken down, where nutrients are released back into the water column, and where much of the carbon that was fixed at the surface by photosynthesis is either remineralized back into dissolved form or incorporated into the bodies of deep-sea organisms. The agents of this transformation are bacteria and archaea, two of the most ancient and most abundant forms of life on Earth, thriving in conditions that would be instantly lethal to almost anything more complex. In the cold, dark, high-pressure environment of the deep ocean, these microorganisms perform the essential chemistry of decomposition, breaking down complex organic molecules into simpler components, releasing carbon dioxide, nitrogen, and phosphorus back into the water in forms that can eventually be returned to the surface through upwelling and used again by phytoplankton in the sunlit zone above. This microbial respiration in the deep ocean is not a footnote to the carbon cycle. It is a central chapter of it. Without these decomposers, organic matter would accumulate on the seafloor unprocessed. Nutrients would be permanently locked away from the productive surface waters where they are needed, and the entire biological machinery of the ocean would gradually run down for lack of the raw materials that only decomposition can provide. The cycle is elegant in its completeness. Carbon from the atmosphere dissolves into surface water. Phytoplankton and algae like coccolithophores incorporate that carbon into their bodies as they grow. When they die, their remains sink, carrying the carbon they captured downward through the water column as marine snow. In the deep ocean, bacteria and archaea break that material down, releasing nutrients that eventually return to the surface to fuel the next generation of growth. And the carbon that is not remineralized, that sinks all the way to the seafloor and is buried in sediment, stays locked in the deep for centuries or millennia, removed from the active carbon cycle entirely. It is a system of extraordinary depth and patience. A conveyor not of water alone, but of chemistry, of carbon and nutrients cycling upward and downward through the ocean on timescales that stretch from the seasonal to the geological. It connects the air above the ocean to the mud below it, passing through every layer of life in between, transforming matter and energy at each step with a quiet efficiency that the most advanced industrial process could not begin to replicate. And it has been running, without interruption, for as long as there has been an ocean. Long before the first fish appeared. Long before the first shell was laid down in shallow water. Long before any eye evolved to see the light filtering down from the surface. The carbon cycle of the ocean was already turning, already moving carbon from air to water to deep sediment and back again, already regulating the chemistry of the atmosphere in ways that made the eventual emergence of complex life not just possible, but inevitable. That continuity is worth sitting with for a moment. The same cycle that removes a fraction of the carbon dioxide from every breath exhaled by 7 billion human beings today is the same cycle that helped regulate the Cretaceous atmosphere, that stored carbon during the Cambrian explosion of life, that has quietly been doing its work through ice ages and warm periods and mass extinctions and recoveries. It is one of the oldest continuous processes on this planet, older than any ecosystem we recognize, older than any life form we could name. The ocean has been keeping its accounts in carbon for longer than we can fully imagine. And still, without acknowledgement, without rest, it continues. Something happens in the ocean every single night, and almost no one on the surface world ever thinks about it. As darkness falls and the last light fades from the surface waters, a migration begins. Not the seasonal migration of birds crossing continents, not the long overland journeys of wildebeest or caribou, but a vertical migration, straight up through the water column, rising from the dim mid-water depths toward the surface, driven by a logic as old as life itself. Mid-water animals, the fish, crustaceans, squid, and countless invertebrates that spend their days in the twilight zones several hundred meters below the surface, ascend each night to feed in the richer, more productive surface waters above them. They rise with the darkness, graze on the plankton blooms and the organic richness of the sunlit zone, and then, before dawn, they descend again, retreating back into the cold and the dark before the light returns and the predators that hunt by sight become dangerous again. This daily vertical migration is, by some measures, the largest animal migration on Earth, not in terms of distance, but in terms of sheer biomass. The combined weight of all the creatures making this nightly ascent and descent, across every ocean basin simultaneously, is almost incomprehensibly large. And in making this journey, these animals do something that goes far beyond simply feeding and retreating. They carry carbon. They eat at the surface, incorporating organic carbon into their bodies. They descend to depth. And there, through respiration and excretion, they release that carbon into deep water, effectively transporting it downward, away from the surface in the atmosphere, adding to the biological pump that the phytoplankton and marine snow began. The migration is not just a feeding strategy. It is, inadvertently, one of the ocean's carbon delivery systems. But the chemistry of the deep ocean is more complex than a simple story of carbon sinking and staying. The ratios of the key elements that life depends on, carbon, nitrogen, and phosphorus, change systematically with depth, and understanding those changes tells us something important about how the ocean manages its resources. Near the surface, where productivity is high and organisms are actively growing, the ratios of these elements in organic matter follow a pattern that oceanographers have studied for nearly a century, a relationship known as the Redfield ratio, a remarkably consistent proportion of carbon to nitrogen to phosphorus in marine organic material that reflects the average biochemical composition of ocean life. But as that organic matter sinks and is decomposed by bacteria at depth, the elements are released at slightly different rates, and their relative concentrations in deep water shift. Nitrogen and phosphorus, the critical nutrients for surface productivity, accumulate in the deep ocean over time, carried down by sinking organic matter and regenerated by decomposition, waiting for the upwelling currents that will eventually return them to the surface. The nutrient cycling of the ocean is therefore not a simple, uniform process. It depends on how productive the surface waters are in any given region, how efficiently organic matter is exported downward before it can be remineralized near the surface, and how actively the water column is mixed by currents and turbulence. In highly productive regions with strong export of organic matter and limited mixing, nutrients can become genuinely depleted at the surface even as they accumulate in abundance just a few hundred meters below. In regions of strong upwelling, those deep nutrients return to the light and fuel explosive blooms of phytoplankton. The geography of ocean productivity is, at its heart, a geography of nutrient supply, and nutrient supply is controlled by the physics of mixing and the biology of decomposition, working together in an endlessly variable dance. And then there is a mechanism that operates largely outside this cycle entirely. The microbial carbon pump is one of the more recently recognized and more conceptually fascinating processes in ocean science. It describes the ability of marine microorganisms, bacteria and archaea, primarily, to transform fresh, biologically available organic carbon into forms that are extraordinarily resistant to further decomposition. Through their metabolic activity, these microbes produce complex organic molecules that other organisms simply cannot break down. These molecules don't sink to the seafloor. They don't get exported downward by the biological pump. Instead, they accumulate in the water column itself, dissolved but effectively inert, carbon that has been chemically transformed into a state where it can persist in the ocean for thousands of years without being remineralized back into carbon dioxide. The dissolved organic carbon pool in the ocean that results from this process is one of the largest reservoirs of organic carbon on the planet, comparable in size to the entire atmospheric carbon dioxide pool. And it is maintained not by burial or by sinking, but by the ongoing chemical artistry of the smallest living things in the sea, converting reactive carbon into something durable and ancient, adding it to a reservoir that stores carbon not in the cold sediments of the deep floor but in the water itself, distributed through the ocean's interior in invisible, dissolved form. Together, these processes, the biological pump, the vertical migration, the shifting ratios of nutrients with depth, the quiet alchemy of the microbial carbon pump, shape the distribution of carbon between ocean and atmosphere with a subtlety and a complexity that climate scientists are still working to fully understand. The ocean's carbon storage is not a single mechanism. It is a layered system of interacting processes, each operating on its own timescale, each responding to physical and biological conditions in ways that feed back on one another. And the net result of all of this invisible activity is a planetary climate that runs cooler and more stably than it otherwise would, moderated, as it has always been, by the chemistry of the sea. Deep below all of this cycling and transformation, in the permanent darkness below 1,000 meters, life has found ways to exist that challenge almost every assumption we bring to the concept of living. There is no sunlight here. There has never been any sunlight here, at any point in the history of this part of the ocean. The darkness is not temporary, not seasonal, not something that lifts at dawn. It is absolute and permanent, as reliable as the pressure and the cold. And the creatures that live in this world have not merely adapted to the darkness, they have built entire biological strategies around it, using it, exploiting it, treating it not as an absence but as a resource. Bioluminescence, in the deep ocean, is not remarkable. It is the norm. The majority of animals living below the sunlit zone are capable of producing their own light, and they use it in ways that reflect the specific challenges and opportunities of a world where vision is possible only when you generate the light yourself. Some deep-sea fish carry lures, modified spines or appendages tipped with light-producing organs, dangled in front of their mouths to attract prey that investigates the unexpected glow and finds, too late, that the light was a trap. Others use counter-illumination, producing light on their undersides to match the faint downwelling glow from above, making themselves invisible to predators looking upward from below. Some species flash warning patterns. Some appear to use light for communication within their own species, producing patterns and sequences that may carry information about identity or reproductive status in a language written entirely in photons. The light these organisms produce is almost always in the blue-green range of the spectrum, the wavelengths that travel farthest through seawater, the wavelengths that the eyes of deep-sea animals have evolved to detect with extraordinary sensitivity. The biology and the physics have co-evolved, each shaping the other, producing a visual world in the deep ocean that is simultaneously sparse and highly meaningful, where a single point of light in the darkness carries more information than an entire sunlit landscape might in the world above. But light is only one of the adaptations that make life possible at depth. The physical challenges of the deep ocean go beyond darkness. There is the pressure, crushing, relentless, hundreds of times greater than anything at the surface, and the cold, and the scarcity of food, and the vast distances between productive patches of seafloor or water column. Each of these challenges has driven evolutionary solutions that range from the elegant to the deeply strange. Deep-sea animals frequently lack the rigid internal skeletons or gas-filled swim bladders of their shallow-water relatives. Instead, many have evolved what biologists call hydrostatic skeletons, bodies supported not by bone or cartilage but by the pressure of fluids within them, balanced against the pressure of the water outside. A gelatinous deep-sea creature is not poorly built. It is precisely built for its environment, flexible, pressure-neutral, requiring almost no energy to maintain its shape at depth, and largely immune to the crushing forces that would destroy a more rigid body. At the cellular level, deep-sea fish have evolved chemical solutions to the problem of pressure that are as sophisticated as anything a biochemist might design deliberately. Cell membranes in most organisms are disrupted by extreme pressure, the proteins within them change shape, enzymes lose their function, and the basic machinery of metabolism begins to fail. Deep-sea fish counteract this by accumulating specific small organic molecules. Trimethylamine oxide is perhaps the best known, that stabilize proteins and membranes against pressure-induced deformation. These molecules act as molecular shields, preserving the three-dimensional structure of proteins at depths where the physics of the situation would otherwise make biochemistry impossible. It is, in the most literal sense, chemistry adapted to geology, life solving a physical problem with a molecular solution, generation after generation, across evolutionary timescales that stretched over millions of years until the chemistry was right. In the deepest ocean trenches, in the Hadal Zone, the adaptations become more extreme still. The amphipods that scavenge in the Mariana Trench and other deep trenches, small crustaceans, resembling elongated shrimp, able to survive at pressures that would instantly kill most other multicellular life, have been found to carry specific communities of bacteria within their digestive systems. These bacterial partners are not incidental passengers. They appear to play an active role in the amphipod's ability to process the food available at these extreme depths, helping to break down compounds that the amphipod's own enzymes cannot handle alone. It is a partnership born of necessity in the most extreme environment on Earth, a microbe and a crustacean, working together in the cold and the dark at the bottom of the deepest trench on the planet, each making the other's survival possible in ways that neither could manage alone. And even in the chemistry of the deep ocean itself, life has found niches that seem, at first encounter, almost impossible. Carbon monoxide, a gas toxic to most life, produced in small quantities by the photochemical breakdown of organic matter in surface waters and mixed downward through the water column, does not simply accumulate in the deep ocean, even though it has no obvious biological consumer there. Specialized microbes, identified only in recent decades of ocean research, consume carbon monoxide as an energy source, using it in metabolic pathways that extract chemical energy from what would otherwise be a waste product. These organisms don't need sunlight. They don't need organic carbon from the surface in the conventional sense. They tap directly into the chemistry of the water around them, turning a toxic gas into fuel. They are a reminder of something that the deep ocean teaches repeatedly, in one form after another, to anyone paying attention. Life does not wait for ideal conditions. It does not require the warmth and light and nutrient richness that we associate with abundance at the surface. Given time, and the deep ocean has had enormous amounts of time, life finds a way into every chemical gradient, every physical extreme, every dark and pressurized and seemingly inhospitable corner of the world. The deep ocean is not a dead place. It is one of the most inventive living places on Earth, shaped by challenges that have no equivalent in the sunlit world above, populated by organisms that solve those challenges in ways that took hundreds of millions of years to perfect. And most of it, we have never seen. There is a tendency, when we think about the deepest parts of the ocean, to imagine them as empty. Cold, dark, impossibly pressurized, places where the conditions are so extreme that life would struggle to gain any foothold at all. The Hadal Zone, those great oceanic trenches plunging to depths of 6, 7, 8, even 11 kilometers below the surface, seems at first like a world defined entirely by what it lacks. No light. No warmth. No connection to the productive surface above. Just pressure and silence and the slow accumulation of sediment over geological time. That picture is wrong in almost every particular. The Hadal trenches are not empty margins of the ocean. They are, in ways that scientists are only beginning to fully appreciate, hotspots, places where biological activity concentrates rather than fades, where organic material funnels in from the surrounding seafloor and accumulates in the V-shaped geometry of the trench, where the very features that make these places so extreme also make them unexpectedly rich. A trench is, in physical terms, a trap. Sediment and organic particles settling across a wide area of surrounding seafloor gradually migrate toward the lowest point, the deepest axis of the trench, where they collect in quantities far exceeding what would settle on a flat abyssal plain. The trench is where things end up, and where things end up, life finds something to work with. The diversity of microbial life that has been discovered in Hadal sediments over the past 2 decades has genuinely surprised the scientists studying it. More than 7,000 new microbial species have been identified in deep ocean environments in recent years, many of them from trench sediments and Hadal waters, and the process of discovery is far from complete. Each new sample brought up from these depths, each carefully preserved core of sediment extracted from the trench floor, contains communities of microorganisms that are, in many cases, found nowhere else on Earth, organisms that have been isolated in these extreme environments long enough to evolve along entirely separate lineages. solving the challenges of deep-sea life in ways that are distinct from anything found in shallower water. The sediment communities of the deep ocean are not simply diluted versions of surface microbial communities, the same organisms present in smaller numbers under harder conditions. They are genuinely different assemblages, distinct ecologies shaped by the specific pressures, temperatures, chemical conditions, and food sources of their particular depth and location. A community living in the top centimeter of trench sediment will differ meaningfully from a community living 10 centimeters below the surface of that same sediment, which will differ again from the community living a meter down, in sediment that may have been deposited thousands of years ago and has been slowly processing organic matter ever since. These deep sediment communities are extraordinarily slow by the standards of surface life. Their metabolic rates are a fraction of what you would find in organisms living in warmer, more nutrient-rich environments. Cell division may happen not over hours or days but over years or even decades. An individual microorganism living in deep sediment may be the same individual cell that was present when that layer of sediment was first deposited centuries ago, not because it has found some secret to immortality, but because in conditions of extreme energy scarcity, life slows to a pace that has no equivalent in our experience of the living world. And yet this slow, ancient, patient microbial life is doing chemistry that matters enormously to the rest of the planet. One of the less visible but deeply consequential things that deep-sea microbes do is break down pollutants. Hydrocarbons, synthetic compounds, organic contaminants that enter the ocean from human activity and settle toward the deep. These materials are not simply inert once they reach the seafloor. Microbial communities in deep sediments possess enzymatic capabilities evolved over millions of years to process complex organic molecules, and some of those capabilities happen to be effective on the anthropogenic compounds that have been entering the ocean in increasing quantities over the past century. The deep ocean is not an infinite sink that absorbs pollution without consequence, but it is not entirely passive either. The microbes within it are at work, slowly, on much of what we send down to them. Beyond the living, the deep ocean floor preserves a physical record of time that is almost without parallel anywhere else on Earth. Scattered across the abyssal plains and the flanks of underwater mountain ranges lie polymetallic nodules, rounded, potato-sized concretions of manganese, iron, nickel, cobalt, copper, and other metals that form around a small nucleus, a fragment of shell or bone or mineral grain, by the extremely slow precipitation of dissolved metals from the surrounding seawater. The growth rate of these nodules is one of the most extraordinary numbers in all of geology. They grow at a rate of a few millimeters per million years. Not per year. Not per century. Per million years. A nodule sitting on the seafloor today may have been growing since before the first hominids appeared on Earth. The outermost layer added to it this year is a layer measured in nanometers, a few billionths of a meter. And yet these nodules are real, tangible, pickable up objects, some of them fist-sized, some larger, built atom by atom across timescales that the human mind cannot intuitively grasp but the deep ocean accommodates without any particular difficulty. They are, among other things, archives. The chemical composition of each layer of a polymetallic nodule reflects the chemistry of the seawater at the time that layer was deposited. Reading inward from the outer surface toward the nucleus is reading backward through time, through glacial cycles, through periods of ocean anoxia, through changes in ocean circulation and productivity and chemistry that are otherwise difficult to reconstruct. The deep ocean floor is a library, and the nodules are among its most precise and long-running records. The sediment itself serves a similar archival function. Deep-sea sediment cores, cylinders of compressed sediment extracted by research vessels lowering coring devices to the seafloor, have provided some of the most important records we have of past climate, past ocean chemistry, past ice volume, and past biological productivity. A single meter of deep-sea sediment might represent 10,000 years of continuous deposition, each millimeter a snapshot of ocean conditions at a specific moment in the past, preserved with remarkable fidelity in the cold, still, undisturbed darkness of the deep floor. The ocean remembers. Long after the events themselves have faded from every other record, long after ice cores have compressed beyond resolution and tree rings have rotted away, the deep seafloor keeps its own account, silent, patient, and extraordinarily detailed. Now, within this ancient and slowly turning world, one of the most fundamental chemical cycles on the planet is playing out in ways we are only beginning to understand. Nitrogen is essential to all life. It is a component of every protein, every strand of DNA, every molecule of chlorophyll that has ever powered photosynthesis anywhere on Earth. The atmosphere is 78% nitrogen gas, but that gaseous nitrogen is chemically inert, unavailable to most organisms until it is converted into reactive forms like ammonium or nitrate that biology can actually use. The cycling of nitrogen between its inert and reactive forms, between the atmosphere and the ocean and the sediment and back again, is one of the foundational chemical cycles of the biosphere, as fundamental as the carbon cycle, and in some ways even less well understood. In the deep ocean, microbial nitrogen cycling remains one of the significant open questions in ocean science. The basic pathways, nitrogen fixation, nitrification, denitrification, have been known for decades. But the specific organisms carrying out these processes in deep water and hadal sediments, the rates at which they operate, the ways in which they respond to changing conditions, and the overall contribution of deep ocean nitrogen cycling to the global nitrogen budget are areas where our knowledge has been advancing rapidly in recent years, and where substantial uncertainty still remains. Recent deep ocean research has identified 5 entirely new lineages of nitrite-oxidizing bacteria in hadal and deep-sea environments. Nitrite oxidation is a critical step in the nitrification process, the conversion of ammonium first to nitrite and then to nitrate, the form of nitrogen most broadly available to phytoplankton at the surface. Finding 5 previously unknown lineages of organisms performing this function in the deep ocean is not a minor footnote. It suggests that the deep ocean's role in the global nitrogen cycle has been significantly underestimated, that there are major biological players in this cycle that we didn't know existed until very recently. Among the new discoveries, a group of organisms in the genus Ketobacter has attracted particular attention. These microbes, found in hadal sediments, appear to be capable of nitrogen fixation, the conversion of inert atmospheric nitrogen gas into biologically reactive ammonium. Nitrogen fixation has long been considered largely a surface ocean and terrestrial process, driven by specific groups of bacteria and archaea in environments where nitrogen is scarce and the energetic cost of breaking the triple bond of nitrogen gas is worth paying. Finding nitrogen fixers in the Hadal zone, in sediments kilometers below the surface, suggests that the deep ocean may be contributing to the global supply of reactive nitrogen in ways that have not been accounted for in existing models. The implications of this are significant. Reactive nitrogen availability is one of the primary controls on ocean productivity, on how much phytoplankton can grow, how much carbon can be fixed at the surface, how much oxygen can be produced. If the deep ocean is generating reactive nitrogen through microbial fixation at rates we haven't previously recognized, and if that nitrogen is eventually returned to the surface through upwelling currents, then the contribution of Hadal microorganisms to the productivity of the surface ocean may be real and meaningful. A connection between the deepest trenches and the sunlit zone above that runs not through food webs or physical transport alone, but through chemistry. It is a humbling thought. The microbes at the bottom of the Mariana Trench, living under pressures that crush steel, and sediments that have been accumulating since before the age of the dinosaurs, cycling nitrogen through metabolic pathways that we are still in the process of discovering, these organisms are participating in the same global chemical system that determines how much life the ocean surface can support, how much oxygen enters the atmosphere, how much carbon is drawn down from the air. The deepest and the shallowest parts of the ocean are connected, not just by the slow movements of water over centuries, but by the chemistry of the smallest living things on Earth, passing elements through their bodies in the dark and releasing them, eventually, back into a world that has no idea they exist. The Hadal zone is not the end of the ocean. It is not the place where the ocean runs out of things to do or ceases to matter. It is, in many respects, one of the places where the ocean's most fundamental and least visible work is being done, slowly, in the cold, under pressure that would be instantly lethal to any creature living in the sunlit world above, by organisms so small that millions of them could fit on the period at the end of this sentence. And we have named, so far, only a fraction of them. Nitrogen moves through the ocean in ways that took decades of careful scientific work to even partially understand, and there are chapters of that story still being written today. We tend to think of ocean chemistry in terms of the elements we can see the effects of, the carbon that drives climate, the oxygen that sustains life, the nutrients that feed blooms of phytoplankton visible from space. Nitrogen is less visible in its workings, more hidden in the fine-grained chemistry of the water column and the sediment, operating through microbial processes so small and so chemically subtle that the tools required to study them have only existed for a few decades. And yet nitrogen cycling in the ocean is as fundamental to the functioning of the biosphere as anything we have discussed, and the microbes performing it are among the most consequential organisms on Earth. In the deep ocean, one of the foundational steps in the nitrogen cycle is ammonia oxidation, the conversion of ammonium, a form of nitrogen released by the decomposition of organic matter, into nitrite. This process happens throughout the water column, but it takes on particular importance in deep waters where organic matter from the surface has been decomposing for months or years during its long descent, releasing ammonium as it breaks down. The microorganisms performing this conversion in the dark, cold, high-pressure environment of the deep ocean are doing so under conditions far removed from the warm, well-lit environments where nitrogen cycling was first studied and understood. They have adapted to their circumstances in ways that are still being characterized, carrying out essential chemistry in a world where almost every physical parameter is pushed to an extreme. Sulfate reduction adds another layer of complexity to the picture. In marine sediments, where oxygen has been fully consumed by the respiration of organic matter in the uppermost layers, bacteria that use sulfate as a terminal electron acceptor, effectively breathing sulfate the way surface organisms breathe oxygen, become the dominant metabolic force. The rate and character of sulfate reduction changes systematically with depth in the sediment, reflecting the declining availability of organic matter as you move further from the sediment surface into layers deposited hundreds or thousands of years ago. In the youngest, most organic-rich surface sediments, sulfate reduction proceeds rapidly. Deeper, in older and more depleted sediment, it slows to rates almost too low to measure by conventional means. The chemical gradient created by this process, sulfate declining with depth, sulfide accumulating, shapes the entire chemistry of the sediment pore water and influences which other microbial processes can occur and where. Within this chemically layered world, nitrite oxidizing bacteria occupy niches defined with remarkable precision. Different lineages have evolved to thrive under different combinations of temperature, pressure, oxygen availability, and substrate concentration, partitioning the environment among themselves in ways that allow multiple related organisms to coexist without directly competing. One lineage may dominate in the cold, well-oxygenated waters of the deep Atlantic. Another may be better suited to the low oxygen conditions found in oxygen minimum zones. A third may be most competitive in sediments at a specific depth range. The ecological diversity within this single functional group, organisms all performing the same basic chemical reaction, reflects the extraordinary variety of conditions found across the global deep ocean. What makes nitrite oxidation particularly significant, beyond its role in the nitrogen cycle, is its connection to carbon fixation. Nitrite oxidizing bacteria are chemolithotrophs, organisms that derive energy not from sunlight and not from the breakdown of organic molecules, but from the oxidation of inorganic chemicals. When a nitrite oxidizing bacterium converts nitrite to nitrate, it extracts a small amount of chemical energy from that reaction, and it uses that energy to fix inorganic carbon from the surrounding water, to take dissolved carbon dioxide and build it into organic molecules, the way a plant uses sunlight to build sugars from air. This dark carbon fixation, happening in the absence of any light, driven purely by the chemistry of nitrogen oxidation, contributes between 15 and 45% of the inorganic carbon fixation occurring in the deep ocean. That is not a trivial fraction. In a part of the ocean that was long assumed to be entirely dependent on organic carbon raining down from the surface, a substantial proportion of new organic matter is actually being generated in place, in the dark, by microbes harvesting energy from nitrogen chemistry. The deep ocean is not merely a consumer of surface productivity. In ways we didn't recognize until recently, it is a producer in its own right. In the oxygen minimum zones, those layers of the water column, typically at intermediate depths of several hundred meters, where the combination of organic matter decomposition and poor ventilation reduces oxygen concentrations to near zero, the nitrite oxidizing bacteria found are a distinct and unusual group. These organisms have adapted to function in conditions of extreme oxygen scarcity, performing their oxidation reactions at oxygen concentrations orders of magnitude lower than those required by their relatives in better oxygenated waters. They have essentially re-engineered the sensitivity of their oxygen-handling biochemistry, allowing them to extract the tiny amounts of oxygen present in these zones with an efficiency that other organisms cannot match. The enzyme at the center of nitrite oxidation, nitrite oxidoreductase, turns out to be capable of something that surprised researchers when it was first clearly demonstrated. Under certain conditions, particularly low oxygen conditions, this enzyme can run in reverse. Instead of converting nitrite to nitrate by adding an oxygen atom, it can strip an oxygen atom from nitrate and convert it back to nitrite. This reversal means that in oxygen minimum zones and other low oxygen environments, the same enzyme that normally produces nitrate can instead consume it, feeding nitrite into anaerobic nitrogen cycling pathways and connecting the nitrite oxidation process to the broader network of nitrogen transformations in ways that make the overall system considerably more flexible and interconnected than a simple linear pathway would suggest. Biochemical reversibility of this kind is not a failure of specificity. It is an evolutionary achievement, an enzyme sophisticated enough to respond to its chemical environment and adjust its direction accordingly, participating in different parts of the nitrogen cycle depending on what the local conditions require. And it is in those same low oxygen environments, and in the deep sediments of the most extreme ocean trenches, that one of the most consequential discoveries in modern ocean science was made, a discovery that fundamentally revised our understanding of how the ocean manages its nitrogen budget. Anaerobic ammonium oxidation. ANAMOX. The process was predicted theoretically on thermodynamic grounds before it was ever observed in nature. Chemists recognized that the combination of ammonium and nitrite should, in principle, be able to yield energy under anaerobic conditions. But for years the prediction remained purely theoretical, because no organism performing this reaction had ever been found. When ANAMOX bacteria were finally identified in the early 1990s, first in wastewater treatment systems and then, critically, in marine sediments and oxygen minimum zones, they represented a genuinely new branch of microbial metabolism, a process that had been occurring in the ocean for perhaps billions of years without any human awareness of it. The reaction that ANAMOX bacteria perform is chemically elegant. They combine ammonium and nitrite in the absence of oxygen, producing nitrogen gas as the end product. The nitrogen gas, being inert and gaseous, escapes from the water and enters the atmosphere, permanently removed from the reactive nitrogen pool of the ocean, lost to the biosphere until nitrogen fixation somewhere converts it back into a usable form. In terms of the ocean's nitrogen budget, ANAMOX turns out to be enormously important. These bacteria are responsible for up to 50% of the total loss of reactive nitrogen from the ocean, the conversion of biologically available nitrogen back into inert atmospheric gas. In some regions and environments, the fraction is even higher. For decades, conventional denitrification, the reduction of nitrate to nitrogen gas by a different group of bacteria under anaerobic conditions, was believed to be the primary pathway by which the ocean lost reactive nitrogen. ANAMOX, once recognized, forced a significant revision of that understanding, roughly doubling the estimated rate of marine nitrogen loss and redistributing the accounting between two processes that had very different dependencies on organic carbon availability and oxygen conditions. The implications for the global nitrogen cycle were substantial. Models of ocean productivity, of the long-term balance between nitrogen fixation and nitrogen loss, of the response of the ocean nitrogen cycle to past and future changes in climate and ocean circulation, all of these required updating once the scale of Anammox's contribution was appreciated. But if the discovery of Anammox in the open ocean and coastal sediments was significant, what has been found in the context of the Hadal Zone has pushed the boundaries further still. In the sediments of the Mariana Trench, at depths exceeding 10 kilometers, Anammox bacteria have been found, not merely present but active, performing their characteristic nitrogen chemistry under pressures that far exceed those in the environments where Anammox was first characterized. Their presence at these depths confirms that the nitrogen loss processes mediated by Anammox extend to the very deepest parts of the ocean, and that the Hadal Zone contributes to global nitrogen loss in ways that are only now being incorporated into our understanding of the nitrogen cycle. More striking still is what has been discovered about the metabolic capabilities of some of these Hadal Anammox organisms. Anammox bacteria are defined by their anaerobic ammonium oxidation. It is the process that gives them their name and their ecological identity. But Anammox bacteria isolated from Mariana Trench environments have been shown to be capable of aerobic respiration as well. They can, when oxygen is present, switch to conventional oxygen-based respiration, a metabolic flexibility that was not expected in organisms so closely associated with anaerobic conditions. This flexibility is not merely an interesting footnote. It speaks to the extreme variability of conditions in Hadal sediments, where oxygen concentrations may fluctuate with the irregular delivery of organic matter and the activity of other microbial communities, and where an organism capable of functioning under both aerobic and anaerobic conditions would have a significant survival advantage. It also complicates the conceptual picture of Anammox bacteria as strictly anaerobic specialists, suggesting instead that at least some lineages have retained or re-evolved aerobic capability as an adaptive response to an unpredictable environment. Benthic nitrogen cycling, the nitrogen transformations occurring in marine sediments, at the interface between the water column and the seafloor, represents what is now understood to be the largest single sink for reactive nitrogen in the ocean. More reactive nitrogen is permanently removed from the ocean in sediments than in any open water process, including the water column Anammox that attracted so much initial attention. The sediment, in its slow and patient way, is the primary place where the ocean completes its nitrogen accounting, where the reactive nitrogen that enters the ocean through fixation and river input is ultimately converted back to inert gas and returned to the atmosphere. This benthic nitrogen processing happens across all ocean sediments, from the shallow coastal muds that receive the richest organic inputs to the deep abyssal plains where organic matter arrives only as the finest and most refractory particles after months of decomposition in the water column above. But the rate is highest where organic matter delivery is greatest, and the range of organisms and processes involved shifts with depth, oxygen availability, sediment age, and the chemistry of the overlying water. What is becoming clear, as more deep and Hadal sediments are sampled and analyzed, is that the biological community performing this nitrogen cycling at depth is neither impoverished nor simply a slowed-down version of what operates in shallower sediments. It is a distinct and specialized community, shaped by millions of years of evolution in extreme conditions, performing essential global biogeochemical functions with machinery that is in some cases fundamentally different from anything found at the surface. The nitrogen cycle of the deep ocean is not a postscript to the nitrogen cycle of the surface. It is not merely the place where surface processes eventually wind down and dissipate. It is an active, complex, and in important ways still poorly understood dimension of one of the most fundamental chemical systems sustaining life on this planet. In the Mariana Trench, in the cold and the pressure and the dark, bacteria too small to see are doing chemistry that shapes the productivity of the sunlit ocean above them, that influences the composition of the atmosphere, that has been running since long before the trench itself was formed by the slow collision of tectonic plates. They do this without any awareness of the scale of what they are part of. They do this because their biochemistry allows them to extract energy from the reactions they perform, and because extracting energy is what living things do. And in doing so, quietly and continuously, they help keep the chemistry of an entire planet in balance. To understand how remarkable the Anammox bacteria of the Hadal zone truly are, it helps to look more closely at what they are actually doing at the biochemical level, not just the nitrogen transformations that define them, but the full range of their metabolic capabilities, and what those capabilities reveal about how life sustains itself in the most extreme environments on Earth. Anammox bacteria, like all living things, require energy. In their case, the primary energy currency comes from the anaerobic ammonium oxidation reaction itself, the combination of ammonium and nitrite that produces nitrogen gas and drives their growth. But the details of how they manage their cellular energy, particularly under the conditions of the Hadal zone, reveal a flexibility that goes beyond what was initially expected of organisms so associated with a single, specific metabolic process. These bacteria use carbohydrates as an energy storage mechanism, building and breaking down complex sugar molecules to buffer their energy supply across periods when substrate availability fluctuates. In the deep sediment environment, where the delivery of ammonium and nitrite is not constant but depends on the irregular rain of organic matter from above and the variable activity of surrounding microbial communities, the ability to store energy in chemical form and draw on it when immediate supplies run short is a meaningful survival advantage. It allows these organisms to maintain metabolic activity through lean periods, persisting through intervals of substrate scarcity that might otherwise force dormancy or death. But carbohydrates are not the only alternative energy source available to them. Hadal Anammox bacteria have been found to possess the enzymatic machinery to use cyanate and urea as nitrogen sources. Both of these compounds are relatively simple organic nitrogen molecules, cyanate consisting of just carbon, nitrogen, and oxygen, urea slightly more complex, and both are present in seawater and sediments as breakdown products of organic matter degradation. The ability to use them expands the range of nitrogen compounds these bacteria can draw on, making them less dependent on the specific combination of ammonium and nitrite that defines their primary metabolism. In an environment as chemically variable and organically sparse as Hadal sediment, The ability to use multiple nitrogen sources is not a luxury. It is a resilience strategy, built into the biochemistry over evolutionary time by the consistent selective pressure of scarcity. And then there is the pressure itself. At the bottom of the Mariana Trench, the hydrostatic pressure exceeds 1,000 atmospheres. This is not a condition that most biological molecules tolerate without significant modification. Proteins fold and unfold in response to pressure, with many losing their functional three-dimensional structure at pressures far below those found in the deepest trenches. Cell membranes change their physical properties under compression, becoming less fluid, less permeable to the molecules that need to cross them. The entire physical chemistry of life is different at these depths than it is at the surface, and organisms living there must solve those physical problems at the molecular level just to carry out basic cellular functions. Hadal Anammox bacteria tolerate these pressures, and the reconstruction of 8 complete or near-complete genomes from Hadal Anammox organisms has given scientists a window into how they do it. Genomic analysis reveals specific adaptations in the proteins these organisms produce, modifications to amino acid sequences that maintain protein stability and flexibility under high pressure, adjustments to membrane lipid composition that preserve appropriate membrane fluidity at depth, and the presence of genes whose products appear to assist in managing the cellular stress associated with extreme pressure conditions. 8 genomes is not a large sample by the standards of modern genomics, but each one is a detailed record, a 4 billion base pair instruction manual for surviving in one of the most challenging environments on Earth, written by evolution over millions of years and preserved in the chromosomes of organisms living in mud at the bottom of the deepest ocean. Reading those genomes is, in a real sense, reading the accumulated solutions to problems that no surface organism has ever faced. What those genomes also reveal is something unexpected about the history of these organisms, specifically about when their ancestors first arrived in the Hadal zone and how they got there. The Mariana Trench, in its current form, is approximately 35 million years old, a product of the ongoing subduction of the Pacific Plate beneath the Mariana Plate, a process of geological collision and descent that has been slowly deepening the trench over tens of millions of years. But the Anammox bacteria living in its sediments today appear, based on phylogenetic analysis of their genomes, to belong to lineages whose origins predate the trench itself. Their evolutionary history extends back further than the geological feature they now inhabit, meaning that the ancestors of these organisms were not present when the trench was formed, waiting to colonize a new habitat. They arrived later, from elsewhere. The most likely scenario, based on the genomic and biogeographical evidence available, is that Hadal Anammox bacteria descended from populations living in shallower sediments, continental margin environments, perhaps, or the upper abyssal plain, that gradually colonized deeper environments as their descendants evolved the adaptations necessary to survive at increasing depths and pressures. The trench was not colonized in a single event but through a gradual process of range expansion, each generation pushing slightly deeper, each population that survived at greater depth serving as the source for further expansion into the extreme. This kind of gradual depth colonization is consistent with what is known about other deep-sea organisms, the general principle that the Hadal zone has been colonized from above, by organisms pre-adapted to deep conditions in intermediate environments, rather than by organisms that originated in the hadal zone itself. The extreme adaptations of hadal life are not innovations that arose in the trench. They are refinements and extensions of adaptations that developed in deep but less extreme environments, honed further by the additional selective pressures of the hadal zone over millions of years. The ancestors of today's Mariana Trench Anammox bacteria were, in other words, ordinary deep-sea microbes, by the standards of the deep sea, before the pressures and isolation of the trench shaped their descendants into something more specialized. The trench took organisms already equipped for the deep and made them into something capable of surviving conditions that would destroy everything else. And through their nitrogen cycling, these organisms reach beyond the trench itself, affecting ocean chemistry in ways that eventually touch the carbon cycle and, through it, the composition of the atmosphere. The connection is indirect but real. Reactive nitrogen availability controls how much phytoplankton can grow in the surface ocean. Phytoplankton growth controls how much carbon dioxide is drawn down from the atmosphere through photosynthesis and how much organic carbon is exported to the deep through the biological pump. By removing reactive nitrogen from the ocean through anammox, converting ammonium and nitrite to inert nitrogen gas, hadal bacteria influence the total pool of bioavailable nitrogen available to the surface ocean, contributing to the constraints on surface productivity that in turn determine the ocean's capacity to absorb atmospheric carbon dioxide. The chain of consequence is long and diffuse, from a bacterium in trench sediment, to the nitrogen budget of an ocean basin, to the productivity of surface waters thousands of kilometers away, to the concentration of carbon dioxide in the atmosphere above. Each link in that chain is real, measurable in principle, and increasingly recognized in the biogeochemical models that scientists use to understand how the ocean functions as a whole. The deep ocean is connected to the surface not only by the slow physical movements of water over centuries, but by the chemical consequences of microbial activity in its most extreme and least accessible environments. What happens in the hadal zone does not stay in the hadal zone. And now, the ocean that contains all of this, the ancient circulation, the microbial chemistry, the carbon storage, the nitrogen cycling, the remarkable life in permanent darkness, is changing. Not on geological timescales. Not slowly, in the patient way that continents drift and trenches deepen and polymetallic nodules grow millimeter by millimeter across millions of years. But on human timescales, in decades, in years, in the span of a single lifetime. The ocean has been absorbing heat since the industrial era began. The physics of this process are straightforward. The ocean covers most of the planet's surface, it has an enormous heat capacity, and as the atmosphere accumulates excess energy from the enhanced greenhouse effect, the ocean is the primary recipient of that energy. What has changed in the past several decades is the rate and the scale at which this absorption has been occurring. Since 1960, ocean heat content has risen dramatically across all depth layers. The surface ocean warmed first and fastest, but the signal of increased heat content has penetrated progressively deeper over time, carried downward by the same mixing and circulation processes that distribute heat through the ocean interior under normal conditions. The warming is not confined to the surface. It is reaching into the intermediate depths and, with a lag measured in decades, beginning to influence the deep ocean as well. In 2025, the ocean absorbed 23 zettajoules of heat. The number is almost impossible to relate to anything in ordinary human experience. A zettajoule is 10 to the 21st joules, a 1 followed by 21 zeros. 23 of them is a quantity of energy so large that expressing it in more familiar units produces numbers that cease to be meaningful at any intuitive level. To put it in terms that at least gesture toward scale, this is orders of magnitude more energy than the entire global human civilization uses in a year, deposited not into machines and buildings and infrastructure but directly into the ocean, added to the thermal content of a body of water that is already the largest heat reservoir on the planet's surface. And the distribution of this warming is not uniform. 16% of the ocean surface reached record heat levels in 2025, areas of ocean where the surface temperature was higher than it had ever been recorded at that location, in some cases by margins significant enough to affect the marine ecosystems depending on specific temperature ranges to function. 16% of the ocean surface is an enormous area. The ocean covers more than 360 million square kilometers. 16% of that is approaching 60 million square kilometers, an area of record-breaking ocean warmth roughly equivalent to the combined land area of North America, Europe, and Australia. These are not abstract numbers. Record sea surface temperatures have direct consequences for the organisms and processes that have evolved in the context of the temperature ranges of the past several thousand years. Coral bleaching occurs when water temperatures exceed the thermal tolerance of the symbiotic algae that live within coral tissues. The algae are expelled, the coral whitens and, if temperatures remain elevated long enough, dies. The geographic range of bleaching events, and the frequency with which any given reef experiences heat stress, has shifted measurably over the past 4 decades in response to rising ocean temperatures. The distribution of marine species is moving. As surface waters warm, organisms adapted to specific temperature ranges are tracking those ranges toward the poles, appearing in latitudes where they were not previously found and disappearing from waters that have become too warm. The ecology of ocean regions is shifting in real time, sometimes gradually, sometimes in abrupt reorganizations triggered by years of unusual heat or other extreme conditions. The ocean that has sustained this planet's climate for hundreds of millions of years, that has absorbed carbon, moderated temperatures, produced oxygen, driven weather, and quietly supported the chemistry of life through ice ages and warm periods and the rise and fall of entire marine ecosystems, is now absorbing the consequences of what humanity has added to the atmosphere in the span of just a few industrial centuries. It continues to do its work. The circulation still moves. The carbon still cycles. The microbes in the hadal sediments still convert ammonium to nitrogen gas in the cold and the dark. But the conditions under which all of that work is being done are changing, and the ocean, patient and vast as it is registering every degree of that change in its chemistry, its biology, and its physical structure. The record is being written in real time now, in warming water and shifting species ranges and the slow, cumulative heat content of a sea that has been asked to absorb more than it has had to hold in a very long time. The warming of the ocean is not happening evenly. Across the vast surface of a planet mostly covered by water, different ocean basins are responding to the accumulation of excess heat in different ways, at different rates, in different depth layers, and understanding that variation is as important as understanding the overall trend. The ocean is not a single body warming uniformly from surface to floor. It is a collection of interconnected systems, each with its own circulation, its own heat capacity, its own relationship to the atmosphere above and the deep water below, absorbing and distributing the energy being added to the climate system according to its own particular physics. The Pacific Ocean and the Southern Ocean together hold the majority of the excess heat that has accumulated in the ocean since industrialization began. This is not an accident of geography. The Pacific is simply the largest ocean on Earth, covering more than a third of the planet's total surface area, and its sheer volume gives it an unmatched capacity to absorb and store thermal energy. The Southern Ocean, encircling Antarctica, is one of the most intensely mixed bodies of water anywhere on the planet. Strong westerly winds drive continuous overturning of the water column, bringing deep water to the surface and subducting surface water downward with an efficiency that no other ocean region matches. That mixing makes the Southern Ocean extraordinarily effective at drawing heat downward, out of the surface layer and into the interior, where it accumulates in the intermediate and deep waters that underlie the roaring 40s and the furious 50s. In the period between 2024 and 2025 alone, the Pacific Ocean contributed 14.2 zettajoules of heat to the total increase in ocean heat content. That single number, from a single ocean basin across a single year, represents a quantity of thermal energy that exceeds the total energy output of human civilization many times over. It is a measure of the scale at which the ocean operates as a physical system, and a measure of how much energy the climate system is currently accumulating. The Atlantic Ocean, during this same period, showed a negative contribution to the overall change in ocean heat content. Its heat content actually decreased slightly, a result of the complex interplay between its own circulation patterns, the strong northward heat transport of the Atlantic overturning circulation, and the particular meteorological conditions of those years. This does not mean the Atlantic is cooling in any long-term sense. The multi-decadal trend of Atlantic warming is clear and ongoing. But it illustrates something important about how ocean heat content changes from year to year. The signal is not smooth or monotonic. It fluctuates with the natural variability of ocean circulation, with shifts in wind patterns and current positions, with the movement of warm water masses from one region to another. Underneath that variability, the long-term trend of accumulation continues, but in any given year, any given basin may gain or lose heat relative to the previous year, depending on where the circulation has moved energy to and from. Heat is not stored uniformly through the ocean's depth either. The surface layer, mixed by wind and in direct contact with the warming atmosphere, responds most quickly and shows the largest temperature anomalies. Below the mixed layer, in the thermocline where temperature drops sharply with depth, warming is slower but measurable and ongoing. The intermediate waters, those masses of water that subducted from the surface decades ago and are now circulating through the ocean interior at depths of several hundred to 1,000 meters, carry with them the thermal signature of the surface conditions at the time they sank, warming progressively as the surface temperatures from which they form have risen over time. And even the deep abyssal waters, those vast cold pools sitting at depths of 3 to 5 kilometers that were once considered essentially insulated from surface changes on any timescale shorter than centuries, are now showing measurable warming signals. The penetration of anthropogenic heat into the abyssal ocean is slower and more attenuated than in shallower layers, but it is real. Water masses that are currently forming at the poles, the same dense, cold waters that drive thermohaline circulation, are forming at temperatures slightly higher than those of previous decades, and as those water masses spread through the deep ocean over the coming centuries, they will carry that additional warmth into environments that have been thermally stable for far longer than modern human civilization has existed. The deep ocean, in other words, has not yet fully felt the warming that is already committed to it by the greenhouse gas concentrations already present in the atmosphere. What is happening at the surface today is the beginning of a thermal signal that will take centuries to propagate fully through the ocean's interior. The deep abyssal waters warming measurably today are responding to surface conditions from decades ago. The surface conditions of today will be felt in the abyss in the centuries ahead. This is the long memory of the ocean expressing itself in a new context. The same slow, patient timescales that make the deep ocean such a remarkable archive of geological history now becoming the timescales across which the consequences of rapid surface change will propagate into the deepest and most ancient waters on Earth. And while the heat accumulates, something else is changing in the ocean, something less visible than temperature, less easily measured than heat content, but in its own way just as consequential for the living world of the sea. The ocean soundscape is falling out of balance. Throughout this entire journey, from the surface waters where phytoplankton produce half of Earth's oxygen, through the mid-water depths where animals migrate nightly between darkness and light, down through the crushing pressures of the hadal zone where ancient microbes cycle nitrogen in the cold, sound has been present as a fundamental dimension of ocean life. Whale calls carrying thousands of miles through the Sofar Channel. Reef crackling guiding larvae home. Bioluminescent conversations in absolute darkness. The faint murmur of plankton blooms. The geological drumbeat of undersea volcanoes. That soundscape, that rich, layered, ancient acoustic world, is being disrupted. Human-made noise in the ocean has increased dramatically over the past century, and particularly over the past several decades. The primary sources are familiar even if their underwater consequences are not: commercial shipping, the low-frequency drone of thousands of large vessels moving continuously across every major ocean route, seismic surveys, sending powerful acoustic pulses through the water in search of subsea oil and gas deposits, military sonar, underwater construction, the increasing industrialization of coastal and offshore environments. These sounds don't stay near their sources. They travel, exactly as the whale calls travel, exactly as the volcanic rumbles travel, through the same physical properties of seawater that make the ocean such an effective medium for acoustic transmission. The result is a baseline noise level in many parts of the ocean that is now measurably higher than it was a century ago. In heavily trafficked ocean regions, the continuous low-frequency hum of shipping traffic has raised the ambient noise floor to levels that interfere with the acoustic communication of large whales, particularly the low-frequency calling species like blue whales and fin whales whose vocalizations overlap in frequency with ship noise. These animals rely on sound for everything from finding mates to maintaining contact between mother and calf to coordinating feeding in groups. The effective communication range, the distance over which their calls can be detected above the background noise, has shrunk in the most trafficked ocean regions, in some estimates by factors of 10 or more compared to pre-industrial conditions. This is not a theoretical concern. It is a measured, documented change in the acoustic environment of the ocean, with direct consequences for the behavior and biology of the animals living within it. To understand the full scope of what is happening to the ocean's acoustic environment, and to track how it is changing across different regions and depth layers, researchers have established global monitoring programs designed to listen systematically to the ocean over long time periods. The Year of Quiet study is among the efforts dedicated to building a comprehensive picture of ocean noise, measuring ambient sound levels across multiple ocean basins, tracking the contribution of different noise sources, and establishing baselines against which future change can be assessed. What this kind of systematic listening reveals is not a uniform global problem but a highly variable one. Some ocean regions remain relatively quiet, their soundscapes still dominated by biological and geological sources much as they were before industrial activity began. Others are acoustically crowded, the natural sounds of marine life competing against the continuous human-made backdrop. The geography of ocean noise pollution maps closely onto the geography of maritime trade and offshore industrial activity, dense along the major shipping lanes, concentrated near coastal development, thinner in the remote stretches of the Southern Ocean and the Central Pacific that commercial routes rarely cross. But the degradation of the ocean's acoustic environment is not only a story of human-made noise adding to natural sound. It is also a story of natural sound disappearing. Ocean acidification, the progressive decrease in ocean pH resulting from the absorption of carbon dioxide and its conversion to carbonic acid, is changing the physical properties of seawater in ways that affect how sound moves through it. More acidic seawater absorbs certain sound frequencies more efficiently, meaning that the ocean of the future may, in some frequency ranges, be somewhat quieter than it would otherwise be. But the biological consequences of acidification tell a different story about sound. Coral reefs are among the most acoustically rich environments in the ocean. The crackling of snapping shrimp, the calls of reef fish, the subtle sounds of hundreds of species going about their lives in the complex three-dimensional structure of a healthy reef, these sounds form the acoustic signature that guides larvae home, that helps juvenile fish locate suitable settlement habitat, that signals to passing animals that this place is alive and productive. As acidification weakens coral skeletons, as bleaching events kill coral tissue, as the structural complexity of reefs declines under thermal and chemical stress, the biological community supported by that structure diminishes. And as the community diminishes, the sounds diminish with it. Degraded reef habitats are quieter than healthy ones, measurably, significantly quieter. Acoustic monitoring of reefs before and after bleaching events shows the loss of the high-frequency biological crackling that characterizes healthy coral ecosystems, replaced by a flatter, simpler soundscape that carries less information and provides weaker guidance to the larvae that need it. Silent reefs are, in this sense, doubly damaged, not only losing the organisms that produce the sound, but also reducing the acoustic cues that would help new generations of those organisms find their way back. Degraded coastal habitats, seagrass beds stripped of their inhabitants, mangrove forests cleared for development, rocky shores where fishing pressure has removed the species that once filled the acoustic space, create stretches of silent coast where sound-based navigation and communication break down. The ocean near heavily impacted coastlines becomes acoustically impoverished, a simplified soundscape reflecting a simplified ecology. And in the deep ocean, the future acoustic environment may change in another direction entirely. As ocean temperatures rise and acidification progresses, the physical properties of seawater will shift in ways that affect how sound travels through the water column. Modeling studies suggest that by the end of this century, under high-emission scenarios, changes in temperature, salinity, and chemistry could allow sound to travel up to 70% farther in some ocean regions than it does today. The so-far channel will shift in depth and character. The acoustic geometry of the deep ocean will be different, not silent, but reorganized, with sounds traveling farther and reaching places they don't reach today, potentially disrupting acoustic environments in remote areas that have so far been spared the direct influence of human-made noise. An ocean in which sound travels farther is not automatically a better acoustic environment. For animals that rely on the current acoustic geography of the ocean, that have evolved communication systems, migration routes, and foraging strategies calibrated to the specific way sound moves through today's ocean, a changed acoustic environment represents a changed world, one that their biology may or may not be equipped to navigate. We called it the Silent Ocean. For most of human history, that seemed like a reasonable description. The surface was wind and wave and occasional cry of seabird. What lay beneath appeared simply still, simply dark, simply inert. The ocean is backdrop, not participant. The ocean is obstacle, not ecosystem. The ocean is resource, not system. But beneath the surface, at this very moment, currents are moving continents of heat from the tropics toward the poles, distributing energy across the planet with a patience and a scale that no human engineering has ever approached. Microbes too small to see are reshaping the chemistry of Earth, cycling nitrogen and carbon through reactions that have no equivalent on land, sustaining the productivity of the sunlit ocean from the darkness of sediments deposited thousands of years ago. Bioluminescent creatures are navigating absolute darkness with a vocabulary of light. Ancient Animox bacteria are converting reactive nitrogen to gas in the crushing cold of the deepest trenches, influencing the atmosphere of a planet they have never seen. Whale calls are traveling thousands of miles through a natural acoustic channel built by physics. Marine snow is falling continuously through the water column, carrying carbon from the air into the deep, as it has fallen every day for hundreds of millions of years. The greatest mystery of the ocean is not whether it is silent. It was never silent. The greatest mystery is how much is happening in the places we still haven't looked, in the unmapped 95%, in the sediments below the hadal floor, in the microbial communities we have no names for yet, in the chemical processes still operating below the threshold of our instruments and our understanding. The ocean is not a solved problem. It is not a known quantity. It is, still, the largest and most complex system on this planet, and we are only at the beginning of learning to read it. Every fact we have followed through these deep waters, every current, every microbe, every bioluminescent flash, every molecule of carbon stored in the cold, is a doorway into something larger, something older, something still in the process of being understood. The ocean holds the history of this planet, the chemistry of its atmosphere, the stability of its climate, and the majority of its living space. And it holds all of this in silence, not the silence of emptiness, but the silence of depth, of patience, of processes so vast and so continuous that they have no need to announce themselves. They simply continue. As they have always continued. As they will continue long after the last human voice has faded from the shore.